Okay, guys, can you hear me?
Yes, sir.
Yes, sir.
Okay.
Yes,
Yes,
sir.
sir.
Okay. Okay. Yeah. So I think some of you have joined today and missed the class and missed both the classes last week due to this section distribution. But I'll just give you briefly what we have discussed in the last week. Yeah. So what we did basically is we introduced probability as introduced probability as a theory to model uncertain experiment, and we said by uncertain experiment we mean the possible outcomes. The outcomes are not certain, meaning uh, it is not deterministic. Okay, so outcomes are not certain. So now once we have an experiment, we said we can we can consider all possible outcomes as a set, and we denoted it as S or omega, capital omega. And we said this is what is called the sample space of the experiment. And then we said, okay, once we have a sample, so sample space basically what are the sample points here are the elements of the set. So this is a set. So space, call it a space, but in most of the times you will see in future also, sometimes we call a set a space in order to mean that it is just not merely a set, but the elements have another meaning to it. So depending on the context, okay. So then we call it a space. For example, we have seen in math 2, we studied vector space, okay. Although that is a set, but we call it a space because it has certain structure, okay, which is defined on top of that it is a set. Okay, so here also same thing, sample space, it is a set, but it is the elements are associated with an experiment, and elements actually they are the possible outcomes of an experiment. So this is what we said a sample space. So this is a set, and then we said okay, we need to find probability of an event. Okay, and we denoted this set A. This is a set of sets. We call this is set of events. Set of events. And so set of event means elements of. So this is a set of sets. So set of sets because an event is a subset of the sample space. Set and elements are called set of events. So elements are the events. Elements of S of the set A script A, let's say, are subsets. Subsets of the sample space. Uh, this is what we said. And then we said, okay, can any subset be an event? We said, okay, event is a subset of S, but can any subset be an event? Okay, that is a non-trivial question which we will not consider in this course. So for us, event is a subset of S. That is what we considered. And we also said, okay, if we have an event, let's say A, so let's say A, and then we have, let's say B, for example, then we have this A union B is an event, A intersection B is again event, and then complement of, this is complement of A, this is also an event. So we had on some Venn diagrams, we have seen that these are the things which you'll assume, okay, whenever set of events is given to you. And based on that, this concepts of sample space and uh, set of events, we said Okay, we'll define a function which is called the probability measure, which is a to, this is taking value from the a to a 0 1, or you can say it will take non-negative values. So now see, so in a general context, whenever we define a function, we always, let's say we say f is a function from a set, let's say a to b. Then we always define what is fx. Okay, then only we consider that as a function, and then fx is defined as an image of x. But here we said, we did it in a different way. We said this could be any function, any way you want to define. I don't care. Given a set of events, you can define any way you want to define, given a set of events, okay, corresponding to an experiment. But whenever you are defining that function has to satisfy three properties, and we said it three postulates, okay. And the first one is p of a is bigger or equal to 0, so it is non-negative. So it will take values which are non-negative for any a in a. So for any event, the probability measure, the value of the probability, or the functional value, because it is a function after all. So this is a non-negative number, and then we said probability of S itself is equal to 1. Here you see S is a subset of S itself. So we considered S as an event. So the probability of the sample space is 1. And another property, another postulate, so is if we have like A1, A2, this let's say have finite number of mutually exclusive events. Mutually exclusive events. That means they are disjoint. Okay, pairwise disjoint. Exclusive events. Then we said their union will also be an event, and then the probability of that has to be equal to sum of the probabilities. Now I equal to 1 to n. Okay, 1 to k. So see here explicitly we are not defined what is a probability function. It could be anything. Let me see. Let me give you an example. Let's say we are conducting an experiment, very simple experiment, just tossing a coin. So the experiment here is tossing a coin, and then tossing a coin. And then what is the sample space here? We will get either head or tail. So we'll write H and T. This is the sample space. Now you can define that probability. So what are the all possible events here? Let's say. So let's say what are the events here? So the events, let's say this set A. This is could be. We also said that we'll consider null set, which is a subset of S itself, is always an event, and the entire set sum space is an event. And then we also consider this also an event because it's a subset, and this also an event. So these are the possible subsets of S. And now suppose we want to define a probability measure. That means we have to define a function which will satisfy these things, which are called. So these things are called. We said that these are called postulates or axioms. So postulates, or sometimes called axiom. So yeah. So now for this experiment, let's say we have a sample space, we have set of all events, then you can define a function, and then we'll check whether it is a probability or not. Let's say you define probability of all the subsets. Now see, of H, let's say you can
Sir,
define, let's say this up. Yes,
excuse me, sir.
yes, please go ahead.
Sir, can you show the second postulate because your screen was lagging too much. That's why it directly went to the experiment. Second and the third postulate.
Yes, sir.
Can you say it now?
Can you please show the second and the third postulate because it was lagging and it suddenly went to the experiment. So
I'm
second and
showing it.
third
I'm
statement
showing.
is
Sir,
not.
Can
we can
Sir, it
see
is
I?
it
showing,
now, sir.
sir. So we can see.
I'm showing it. Yeah. So this A1, A2, AK, they are mutually exclusive. It means they are pairwise disjoint subsets of S. Then you have this. I mean, this we defined earlier, but I'm just reviewing whatever we have done. You can go through the lecture note, which I uploaded. Unfortunately, I could not upload the lecture 2 because it is always showing that there is an error. Whenever I try to upload it, it shows there is an error. I don't know what it is. So yeah, whenever it will work, let's say I'll be uploading it. But the lecture 2 is also, lecture 2 is also, the video is available, which you can download and can watch if you want to. So yeah, so any function actually, so given the experiment, so that means the set of event is fixed, sample space is fixed, and any function you define which satisfies these three properties, we'll call it a probability measure. So it is up to you how we want to define a probability. Okay. And what we said here, okay, for example, okay, so here we are considering an example. So you can say it here, let's say this is a probability, okay? Probability of phi null set is equal to 0, and probability of, let's say, S is equal to 1. Now say this is a probability because it satisfies all the axioms, okay? These are all non-negative values, first of all, and these are the possible events, H, T, phi means the null set and the sample space itself. But instead of that, this is, a sample space, probability of S is equal to 1, which was the second axiom or second postulate. And of course, disjoint means here, for example, H, this is an event, this is an event, which are disjoint. Then if you take the union, which means S itself, then it is same thing as saying probability of H, okay, plus probability of T. So this is an example of a probability measure. But suppose you can define in a different way also. For example, let's say, let me define it this way. Whatever you want to, let's say, I define it to 1 by 10 to the power 5, 25. Let me define it this way. And probability of T is equal to, what should be this one? 24 by 25. Okay. Now see here, and probability, let me say that this is probability of the null set is equal to 0. And then probability of S is, you see, it is 1. So then this is also a probability measure. So I can define it this way also. So any function which satisfies, you can define anything. Like maybe in a general setup for this simple example, you can consider this to be any A, okay? This to be any some value A, okay? Which is, let's say, lying between 0 to 1, and then probabilities. No, not this A here, but it's, let's say, H here. And then probability of, you can define this to be T, which is equal to some, the remaining part, which is 1 minus A, and where, let's say, A is 0 to 1, whatever number you want to define. And then, of course, probability is already defined. In fact, we also proved the following fact. We also proved that, and not proved, but yeah, this is obvious. We said in the first lecture that this is a fact that, in fact, this is, we mentioned it as a theorem, that if you take any subset of S, then probability of A is nothing but sum of the probability of X over all X in A. This is very simple observation because it due to postulate 3. Now see, what is the postulate 3? If you take a set of disjoint events, okay, and then take their union, then the probability of that union is nothing but a sum of the probabilities of those events. Okay, postulate 3. Postulate 3. So same thing is here. If you take any subset A here, okay, this is any set A, then A can be written as union of all the sets. So this is due to this. Why? Because A can be written as union of all X which are here in A. Yeah, simple. And these are all disjoint. These are all events, and these are all disjoint events. Collection of mutually exclusive events. Then you apply postulate 3, and then you have this result. Okay, so that means we said, okay, so before that we defined two kinds of sample spaces, and we said, okay, there are two kinds of sample spaces. One is, okay, sample space that can be of two kinds. One is called discrete, and another one is called continuous. Okay, continuous. By discrete, what we mean is by discrete, what we mean is that it is S is countable. So S is countable. S is the sample space here. S is countable, and by countable we mean S is either finite or countable infinite, and the rest, if it is not, that means it is uncountable infinite, then it is called continuous. S is uncountable. And we spend a lot of time to decide what it means, but I think, okay, you can spend some time and you can understand what it is. C-U-N, uncountable. Okay, there are two kinds of sets, two kinds of sample spaces here corresponding to an experiment. For example, we gave some examples of when it could be uncountable. For example, we said, suppose we want to measure height. Okay, even if the sample space is finite there, but height can be considered at any value, let's say from 4 to 6 feet, okay, whatever it is. So then we'll say, okay, the sample space could be from 4 to 6, something like that. You measure something, okay, which can take any value, okay, from an interval. Then we say, okay, it is continuous. Okay, the possible outcomes are continuous. And let us say you have some part of your wall in your room you're sitting now, and then you throw your pen on the wall, and then it will hit a point. Now, what is the set number of points on the wall? So that can also be considered as a subset of an XY plane. So it is also uncountable, something like that. So you will get the feeling like when it is countable, when it's not countable. And so these things will be dealt with differently when it is discrete or when it is continuous. But this is the basic difference: sample space when it is discrete and when it is continuous. Yeah, this is the thing which we did in lecture 1, and then we said, okay, then so this is very important thing actually here. This part is very important. That means what is happening here. If we want to define probability of an event, okay, what will be the event? What will be the corresponding experiment? So if you know probability of individual outcomes, possible outcomes, then you can find out probability of the event. That's the first thing to observe here in this fact or in this theorem or whatever you say. Okay, so that means our ultimate goal will be to make a guess depending on the data you are given or depending on the problem you are given. So your first guess will be to decide the probabilities of individual events, okay, of a sample space or of an experiment. Okay, and if of course this problem is a difficult problem, when you have many points, many possible outcomes, this is always always a difficult problem. Okay, given the problem, suppose you have a problem where so many points, okay, I mean, let's say millions or billions of possible outcomes are there, and you need to define, it is not even infinite, it is just finite, but you need to define, let's say, probabilities corresponding to each of these possible outcomes. It is, of course, a challenging task, but here in the classroom situation, we'll have problems which are very simple problems, and you will see that how to define probabilities corresponding to each of these singleton sets or each of the possible outcomes. Okay, and when you apply this thing in a data analysis course or AI or ML, whatever it is, then you will see that this is really a challenging thing. Okay, yeah. So this is what we discussed, and then we said, okay, we will prove some properties of the probability, because those, I mean, using those three postulates, okay, we can derive new properties about probabilities of events, which probably will be used to solve certain problems. Okay, and this is what we said, and we talked about some properties of probability. Okay, so yeah, so then we discussed about some properties. Okay, I was writing properties of probability measure or the probability function. Sometimes I will use the word measure. This, as I told you before, measure has a meaning which probably you will get to know if you do an advanced course on probability theory. But let us say it is measuring something, right? Here it is like measuring something corresponding to some subset. Okay. For example, if it is like, I mean, a measure could be like number of elements of a set. Okay, that could be also a measure. So that gives you a value. Okay, corresponding to a set, number of elements. But here it is not that, because this is different measure, because this value is lying between 0 to 1. So it cannot be the number of elements, but it is something. Okay, it gives a measure. Okay, it is something. Okay, and then we said, okay, we explained certain properties. For example, we said probability of complement of any event is also an event, and 1 minus probability of A. And why we are saying this, why we are discussing this properties, because this properties will be helpful to solve problems. So you will encounter situations, you will encounter problems where maybe you know probability of A, and suppose the question was actually you have to calculate probability of the complement of A. So you can use this formula. You can assume that you can maybe considering, okay, you can consider this as a formula. Okay, but these are all theorems, as we discussed before. And we said also this can also be proved. I mean, this is 0. So probability of the null set is always equal to 0 because of the first property. And then also we said, okay, if we have two events, like let's say A is an event and B is also an event, where a probability where A is a subset of B, then you can say that then if this, then probability of A, this is less equal to probability of B. Okay, and then also we said, okay, this fact can also be proved, but okay, let's say this we define by your assumption this is the case, but this can also be proved. Okay, so we define the probability value. Probability function is the image or the codomain set for the function probability is between 0 to 1, but you can just say it is a non-negative function, and then you can show that it is less equal to, the value is less equal to 1. And then we also okay, so you should mute yourself, okay, because every time I have to go and mute yourself, so it will take some time. There will be a lag. Anyway, so and this is yeah, and then if you have any two subsets, okay, A is a union B. Suppose A and B are any two events, okay, and if they are disjoint, then we know that probability of this event A union B is nothing but probability A plus probability of B. But if they are not, this is due to the postulate 3. But if they are not disjoint, so you have, let's say, some A here and some B here, there is an intersection here. Okay, there is a non-empty intersection here. Then you have to calculate this, and then you can say this can also be proved that this is probability of A plus probability of B minus probability of A intersection B. Of course, if A intersection B is a null set, then we have probability of union B is equal to probability of A plus probability of B, which is postulate 3. Okay, these I think we had done up to this much. And today, uh, I'm getting some echo. Maybe somebody's. Okay, now it is fine, I think. Okay, so today we'll discuss some more properties of probability, and we'll see some examples how those properties of the probability function can be used to solve certain problems. Okay. Okay. So let's say today, my next property for the probability function is the following: 6. So let's say we have 3 sets or 3 events. Okay, they are events. So they are subset of some sample space S. Then I am asking what is the probability of A union B union C. So you can have a general setup. So I mean, this can be proved using this Venn diagram and using a little bit of algebra on sets, which you can do. So I will not prove it, but you can say that this is this probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C plus probability of A intersection B intersection C. So it is like you have this as a sample space. Let's say you have some A, some B, some C. Okay, this is, let's A, this is, and you want to find out the probability of A union A, B union C. So let me just give you, let me discuss a problem where this kind of situation will arise. Okay, so let me discuss a problem. So let's say I have a problem here. Problem is like this. Suppose suppose you visit to a dentist. Okay, so suppose I visit suppose suppose I visit a dentist. Okay, dentist. So, and I know, so if I visit to a dentist, what he or she could do. I have a problem, let's say, in my teeth. So maybe he can suggest me, the doctor can suggest me to clean my teeth. Okay, or maybe there is a cavity and that has to be filled, or maybe some tooth, okay, has to be extracted. Okay, that is also there is also a possibility. Okay, so let us assume that, so I visit to a dentist, and let's say the probability so that the teeth is clean, the teeth will be cleaned, let's say uh, the teeth will be cleaned. Okay, I don't need to write everything, but anyway, so will be cleaned. Let's say it is some number, let's say it is some 0.44. Okay, probability. Okay, and let's say or let's say I'll have cavity filled, cavity filled. Okay, with probability something, let's say 0.21, and maybe some tooth has to be extracted, or let's say, or a tooth has to be extracted. Okay, with probability something, with some probability. Yeah, probability with the remaining ones, so it will be, or maybe, yeah, so let me write it like 2.04, 2.21, something like this. So 4, 4, 8, 9. Okay. Okay. Something, the remaining part maybe. Yeah. Okay. Now let's say also let's say that what is the possibility that my teeth will be cleaned and also the cavity will be filled. Let's say, and also assume that. And so the remaining probability here, you see, the addition of this thing is not 1. So what I'm assuming is that I don't have to do anything. Maybe the doctor will say, okay, don't have to do anything, any of these things. You just take some medicine, you'll be fine. Something like that. And let us say, let us also assume that the probability that the teeth, okay, that teeth will be cleaned, okay, will be cleaned and cavity filled. So a cavity filled is, let's say, 0 point something 08. Now let's say this is one case. Another case could be like the probability that my teeth will be cleaned and some, let's say, a tooth will be extracted. Okay, that will help to have some probability. So cavity filled is this, and let the probability that let's say I will have my teeth cleaned, okay, and a tooth extracted, okay, is let's say 0.11, and let's say another option, let's say the probability that the teeth will be cleaned and let's say a tooth extracted and a tooth extracted, okay, okay, is let's say 0.07. Now what I'm trying to do here is, you see, that I mean, I can have all the remaining options. So what I'm trying to say is that, let's say I define my event to be this, okay, that that my teeth will be clean. This is one event. Another event is that the cavity will be filled, okay. Another event could be that a tooth will be extracted. So these are like A, B, C events. And let's say I want to find out the probability that at least one of this thing will happen, okay, that either my teeth will be cleaned, or I will have cavity filled, or a tooth will be extracted. So then actually I'm looking for, so if I define that event as an event A, that event as some event B, and this event as some event C, then the question is here, let's say, question here is, what is probability of A union B union C? That means what I'm looking at is at least one of these things will be done. So if I want to now say, this is my question, let's say, then so then what I'll do is I would like to use the formula, and for that I need the value of the probability of, so if we just go back, you see the formula. So I need these values, and so these values must be supplied somehow to me. And so if so, that's why I was writing. So if these values are given, that means if A intersection B, for example, if this my teeth will be cleaned as well as a cavity filled, okay, so then I'll have my cavity filled. So that is an event which is A intersection B. And similarly, so you'll have all the probabilities. Once you know all these probabilities, this one, this one, this one, this one, okay, and this one, this one, this one, I know already these probabilities, then I can find out probability of A union B union C, okay. So this is just an example where you can use this particular formula, okay. So whatever formula I said here, like 1, 2, 3, 4, 5, this will be used to solve problems, okay. So in the
Sir,
problem, maybe,
excuse me, sir.
yes.
Sir, sir, can you please again explain that what is the difference? Like, how should we interpret like P of A union B union C and P of A intersection B intersection C? What is the exact difference? I'm not getting.
No, I'm not saying any
Like,
difference here.
hmm,
I am saying A, B, C, they are three events, let us assume.
three events. Hmm.
Okay. They could be mutually exclusive, meaning they could be all disjoint. Then if they are all disjoint events, like you can have a situation like this. This is A, this is B, this is C. Okay. Suppose I say, okay, so the event, okay, that there is a student in this course in let's section A. The probability that there is a student in section A who is studying, let's say, ocean engineering, okay, and let's say there is a student, what is the probability that there is a student, and the event, let's say the number of students here from let's say from electrical engineering, and there is another event, something like that, okay, A, B, C. So then that could be disjoint or could be same, or need not be disjoint. For example, somebody, let's say, electrical engineering plus something, let's say some there is some student who is doing some minor in electrical engineering or minor in mathematics. So there may be some overlap. Okay. So something like that. So maybe the events are all disjoint, or maybe there is some overlap. Okay. So then this is a general situation. This situation is general. If they're all disjoint, then from postulate 3, we already know the value of the probability of happening of either of this, means A union B union C. What is the meaning of A union B union C? either one of this will happen.
Mm.
So
Hmm.
two of them could. So if I just write that X belongs to A union B union C, what does it mean? This is an outcome, and this is a possible event. That means one of these events at least occurred. Okay, either
Okay,
A
sir.
or yeah. So if A, B, C are disjoint, we directly know from the postulate 3 that probability of A union B union C is equal to sum of the probabilities of A, B, and C. So it is the case. Okay, if they're disjoint, then this equals to this one. But if they're not disjoint, okay, it can be proved that then, I mean, it can be proved, but it can be proved using those three postulates. I'm not proving it because it will take a long time. I mean, the proof is also very simple. You just simply use the Venn diagram and three postulates to prove that this is true. Okay, this entire expression is true. So once I have non-empty intersections between the events, that means there are some overlaps, then this is a general formula for finding the probability of A union B union C. And then what I was trying to tell you is that why I am saying all these properties, because when you will encounter some problems, okay, you may be asked to find probability of an event which can be expressed as union of some other events whose probabilities maybe are known due to the given data or due to the given problem. Then you have to use some of these properties, okay, to find the answer, like what is the probability of that corresponding event which can be expressed as union of some other events. And suppose you know some related, so all these probabilities here in this formula, then you can use this entire formula to calculate the probability of the union of those events. You understand now? So I was trying to create a situation, a problem. So for example, if you visit a dentist, so you can have three possible events, and finally maybe you will be asked to find out, okay, what is the probability that either you have to extract a tooth, or maybe your cavity will be filled, or maybe your teeth will be cleaned. What is the probability? That means I'm asking what is the probability about A union B union C. I can find out this using that formula. Okay, I can find the value of this using the formula or the property, provided I have some additional information. So that's why I was giving that additional informations like this, and so on, the probability of the intersection of these things. So if I have all this, so on. So if I have all this information, then I can use this information to calculate what is the value of this number, what is the value of this. Okay, so I was just giving you an example. Okay, so now I'll generalize some of the ideas. So I'll say, okay, there can be some very specific problem. Just a minute. So there can be some specific problem. Now, suppose, okay, so let me give you a situation. Suppose I ask a question like this. What is happening here? Okay, so okay, so let's say if I ask a very general question, let's say, what is the let me ask you a question. Okay. Let me ask you a question that what is the probability that a teacher, okay, teacher means who teaches, okay, in India, let's say, you can say a mathematics teacher also, not a problem, that a teacher, let's say in India, okay, makes more than, let's say, 5 lakhs per year. If I ask this question, okay, what is the probability that a teacher in India makes more than 5 lakhs per year. Basically, what I'm talking about is, suppose if we have a teacher, let's say, so he or she will withdraw some amount of salary per month, okay, and this is 12 month a year. So if you just sum up the salary per month, then what is the total salary per year? Now, if we ask this question, this is, I mean, the answer will vary. Answer will vary means, suppose you consider your own state, okay, or maybe your own district. Then, based on your sample, okay, you can say, okay, I did a survey, and okay, the probability is 0.9, okay, or probability is 0.8, okay. Somebody did it in some other district, okay, and then his or her answer will also be something else. Even if we do that, let us say I want to fix the district also. Suppose there are two students here in this classroom who belong to the same district, or let's say same state. Let's say it's Bihar. Okay. Now I ask you this question: what is the probability that in Bihar a teacher makes more than 5 lakhs a year? Okay. Then also answer can vary. Why? Because you in your sample space, maybe whatever survey you have done, maybe you have sample space, you have considered school teachers, okay, or maybe more school teachers than college teachers, and then the preschool teachers, or maybe university teachers, and maybe now NITs, IIT teachers, and so on. So your answer will vary, okay. So depending on how many sample points are there from which domain means it could be from school, it could be from college, it could be from university, and so on. So it is not specific. So all the answers could be correct or all the answers could be wrong based on your survey. Now, if I make my question much more precise, maybe I could ask, okay, in Bihar, what is the salary of a teacher per year, okay, in an institute or in a school, okay. Now once I make that, we have to supply you with an additional information, the probability value will change, because earlier, let's say, you have considered sample points. That means you have considered teachers who are from all kinds of like school, colleges, and university, and so on. So that means my probability value of an event, okay, can get changed. Okay, the probability value can change if I supply you with an additional information. Okay, what is that information? Let us forget about the question for the time being. This is not the right course to discuss this. But let us say for information in a generic sense. That means I am supplying you with some amount of knowledge, let's say. Okay, again the question is what is knowledge? But let's say which gains some which specifies some particular sample points. Okay, that's the question. That means if you consider all teachers and if you consider a teacher from universities or schools, so that is a subset of that event. Okay, in that sense. So then the answer will vary. So that means my probability will change based on the condition. Okay. So then we have a new concept here, which probably you probably know, which is known as conditional probability. Okay. So conditional probability. Now, what do I need? Why do I need to study this? Because if I'm supplied with an additional information, how does it affect to the probability of that event? Okay. So conditional probability. What we are talking about here, we are talking about an experiment where we have a sample space, we have a set of events, and we have a probability space, which is called, okay, sometimes I will use the word probability space, which we defined in lecture 1, but let me just recall. So this thing is called probability space, or when it is discrete, it is sometimes also called an ensemble. Ensemble. Probably the physics students have heard many times about the word ensemble. Okay, ensemble. So it's a probability space or just an ensemble. So now I already defined conditional probability. So basically what I'm talking about is what is the probability of A given some B, where this is equal to what? How do I calculate this? Okay, when A and B are are events. Okay, events correspond to this experiment, correspond to this probability space, are events. That is A and B, they are all subsets of S. Okay, how do I calculate that? Definitely this will be different from, so from the general knowledge, this will be, so in let's say in a generic sense, in a generic sense, I mean in most of the cases maybe, in a generic sense, that this need not be, it need not be same as probability of A, because I'm supplying you the additional information. But it can be same as well. And then those events are very specific events. Okay, we'll give it a name. Okay, but in general, since I'm supplying you with an additional information, so my guess is, okay, they should change. So that means the occurrence of A depends on the occurrence of B. Okay, so how do I do that? Okay, so the definition is, okay, so you can prove it also using some examples, but let me just clearly give you the definition. I mean, you can do some set theoretic proof of this formula also, but we can consider it as a definition as well. So if A and B are two events, okay, and probability of A is not equal to 0, then the conditional probability of B given A is, let's say, probability of, so I in the last page I had written PA given B, and here I'm writing PB given A, just to keep a note that this need not be same. Okay, so depending on A and B, I can write it like this: A intersection B. This is my definition by probability of A. You can, yeah. Now let us. This is my definition. Now let us solve a problem using this formula. Okay, so why these formulas or these definitions are important? Because again, I will say the same thing. When you encounter a problem in real life, or you encounter a problem in exam or in assignment, okay, you will be asked probably this kind of a question. Then so you have to find a probability of some B given A. Okay, then you have to formulate that question, and you have to identify what are those events, and then possibly you have to use this formula to find out the solution. Okay, so let me discuss a problem here, okay, where this kind of situations could arise, and you have to use this formula to solve the problem. Let's say so I give you a die, okay, die, it's like a die of a Ludo kind of a thing. There are 6 possibilities. Okay, let us say I give you a die. Okay, and let's say this die is a little biased when I say, okay, I did not repeat it today, but for the students who did not attend the first lecture, so in general, the difference between this course or the standard probability theory course or probability statistics course in an undergrad level and whatever we have done during 10+2, like in the class 10th or 11th or 12th class, the fundamental difference is here we define probability as a function. Okay, and we said probability can be defined in different ways, whatever we want, depending on the context. But for plus 2 students, like 10+2 students, probability random, meaning always that this sample space, so the possible point outcomes, in most of the cases, they are all equally likely. So whenever I say you pick something random, okay, randomly, let's say I give you a box which contains 6 numbers and pick any one of them, then we assume that, okay, if I pick the probability that I'll pick, let's say 1 to 6. These are the numbers. So the probability of picking 1 is 1 by 6. Probability picking 2, 1 by 6, and so on. They're all same. So they're all equally likely. Okay, but probability need not be same. Okay, you'll see in different contexts that it did not be same. So let us discuss this problem. Suppose I give you a dice or a die. Okay, I give you a die. It has 6 spaces, and I say that, okay, I designed the die, I have designed this die in such a way that the odd number, the appearance of the odd number is twice as likely, okay, to occur as even number. This is how I designed it. Okay, so let's say, so I let or let's say consider a die. Consider a die. Okay, such that each odd number is twice. Okay, is twice more likely to occur. Okay, to each even number. And whenever I say it is a die, it means I'm talking about a simple die. Okay, even number. Then my question is, okay, I'll give you 3 questions. Then find the probability that, okay, that let's say a number more than 3, okay, or greater than 3, not more than 3, but let's say it's greater than 3. Greater than 3 will occur or occurs will occur on a single die, on a single roll. Okay, this is one question. Let's say my second question is, what is the probability? It's the probability that the number is a perfect square. I mean, the number means the outcome is a perfect square. Once you roll the die, it is a perfect square. Okay, and then let me ask, what is the probability? Probability that the outcome is that the outcome is a perfect square. Okay, given that it is more than 3 or it is greater than 3. Let us say I have this problem. Now, if you want to solve this kind of a problem, okay, if you want to say this kind of problem, as I have been telling you, whenever there is a problem, you always try to fix or decide or determine what is the sample space. Okay, so here it is like rolling a die. Okay, then what is somebody is writing something. 4/9, 1/3, 1/4. Oh, I don't know. I need to check. But let us say I want to solve this problem. Okay. Now, whenever I have a problem like this, I always try to find out what is the sample space. So what is the sample space here? Sample space is set of all possible outcomes. Okay. So here the sample space is 1, 2, 3 up to 6. Okay. And I don't know what is the probability of occurrence of 1 or 2 or 3. Okay, I don't know that, because so the coin is, the die is already biased. It is not, so the probabilities are not equally likely. Like probability of getting 1 is not equal to probability of getting 2, because it says the probability of occurrence of uh, odd number odd is more likely or twice likely to occur even number. So that means what is happening is, if the probability of occurrence, let's say any even number, is x, then probability of occurrence of an odd number is 2x. Okay, and how many odd numbers and how many even numbers are there? There are 3 odd numbers, 1, 3, 5, and there are 3 even numbers, 2, 4, and 6. So if I want to solve this problem, so what I have to first, what do I have to do? So my sample space is, first of all, 1, 2 up to 6, or let's say 1, 2, 3, 4, 5, 6. And then what is given is, like, if let's say if probability of uh, occurrence of an even number is x, then the probability of occurrence of an odd number is 2x. So what is the probability of occurrence of 1? So probability of occurrence of 1 is 1 is odd, so it is x. The probability of occurrence of 2, it is 2 times x. Probability of occurrence of 3 is this. So I know that probability of s equal to 1, which is, as I said before, you remember, I'll use all these properties of all this x. Oh, here, let's say all this, all this, all this, all this, all this s. Okay, where s is an s. So this is my, see, this is one of the properties I said about probability. So that means this is 1 equal to probability of 1 plus probability of 2 plus dot 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 plus probability of 6. So probability of 1 is equal to x. No, it is 2x plus x plus 2x plus x. Okay, plus 2x again plus x again. So I have then 2, 3, 4, 5, 6, 7, 8, 9. It is 9x. So it implies x equal to 1 by 9. So probability of occurrence of an odd number is 1 by 9 and even number is 2 by 9. Okay. So now let us go back to the question. What is the question is? So this was my question. First question was, find the probability that a number greater than 3 will occur on a single row. So greater than 3 means either 4 can appear, 5 can appear, and 6 can appear. So actually the question is, so the question, if we just if we just understand, so the first question is what is probability of this? 4, 5, this is an event. So if 4 occurs, okay, then this event has occurred. If 5 occurs, then also this event occurs. 6 occurs, this is also this event. Then also this. So basically the question is, what is the probability of 4, 5, 6? That means this set, this particular event. This event has occurred means a number greater than 3, okay, has appeared once you roll the die. So then how do you answer this question? Again, use the property. So this will be equal to probability of 4 union probability of 5. So this must be equal to probability of 4, not union, but the sum, probability of 5 plus probability of 6. And I know probability of 4, which is x. See, for odd number it is, for even number I assume that it is x. For odd, it is 2x, and I know value of x, which is 1 by 9. The probability of 4 is x, 1 by 9. Probability of 5 is 2 by 9. Probability of 6 is equal to, again, 1 by 9, so it's equal to 4 by 9. That's my answer. Okay, that's my answer for the first question. Then what was the next question? The next question is, what is the probability that, okay, the next question is this. What is the probability that, THAT, that the number is a perfect square? Now, what is a perfect square? Perfect square means it is a square of a natural number. Now, out of these numbers, 1, 2, up to 6, which numbers are square of another number? Okay, what is the cause? Which number is square of another number? So 1 and 4, they are only the perfect square numbers here. Okay, because 1 is 1 square and 4 is 2 square. So basically, the next question is basically, next question is they're asking what is the probability of 1 and 4? And I know this because this is probability of 1 plus probability of 4. I know what is probability of 1, which is what is probability of 1? 1 is odd. Okay. Yeah. So even number is x. Okay. Odd number is 2x. So odd number is 2x is 2 times 2 by 9 plus 1 by 9. So it's equal to 3 by 9. So is that okay? What I'm doing is okay? Can anybody?
Yes, sir.
Yes, sir.
Oh,
Yes.
okay. Okay.
Yes.
So this 3 by 9. So it is equal to 1 by 3. Okay. So this is the next question. And what was the third question? The third question is, it is, I have to find out the probability of what? What is the probability of the outcome is a perfect square, given that it is a greater than 3. That means basically what happened? Yes. Yeah. So basically the question is, that if A denotes the event, okay, that it is greater than 3, the number appeared is greater than 3, or let's say it is B, okay, let's say, or maybe it is, it doesn't matter, greater than 3, okay, and let's say B is what? Let's say B is perfect square. So what is the question they're asking? They're asking the question, what is the probability of B when A is given? Okay, this is a question they are asking. So it is equal to probability of, according to a formula, this by probability of this. So which is 1 by 9, because A by intersection B is what? Greater than 3 means 4, 5. So which is this 4, 5, 6. This is the event. Perfect square is 1 and 4. So A intersection B is only 4. 4 is even. So its probability is 1 by 9. And probability of A is already known to me. So this is 4 by 9. So the answer is 1 by 4. Okay. So this is a very simple example where you see that how those properties can be used to solve some problems. Okay, like this one. So I'm going a little slow because it is a 2 hours class. Yes, please, somebody has some question. Please go ahead.
Sir, I had a doubt.
Yes.
So why do we exactly divide it? Like, why am I dividing probability of A? Like I'm not
Okay,
even
I'll come.
understanding that.
Okay, it is not a division. I'll come to that. Okay, I'll come to that question. Okay, I mean, not a division means it is a division, but I'll. Okay, so in order to answer his question, what is the meaning of division here? So let us define something called. So basically, the thing is, here I said this. Okay, this is P A intersection B divided by. I mean, I can prove this, but let us say this is my definition because I use that as a definition. This thing, okay? Or I can say this probability of B given A is equal to this probability of A intersection B. Probability of. If I use this as a definition, this or this, okay, and what it means. Let's say this one. Let's say what does it mean? I already assume that P is this, and this means probability of A intersection B is actually equal to probability of B given A times probability of B given A. Now we can prove that this is the thing. Okay, what is the meaning of this? So here is no division. Okay, so what I'm saying here is simple. This is very simple case. Now, suppose I have some, let us say, let me just let's take consider an example. Okay, let us say. So let's just say you go to a shop. Okay, and let us say this is a sort of this is a shop. Let's say it is a television shop. Okay, so there are a lot of televisions, and you want to buy two televisions, one for you and one for your, let's say, parents. Okay, you want to buy two televisions. Okay. Now let us say, okay, let us consider this as a problem then. Okay, let us say, suppose that let's say, okay, let's say, let there be some number of televisions. So there be 240. Okay, any number arbitrary, 40 television sets. It could be any problem, but I'm just television sets. See, the thing is, I mean, in the exam, there could be problem from any different contexts. Okay, so that's why I'm choosing different contexts, because you'll be acquainted to consider different scenarios. Okay, to think about different scenarios. That's why I'm picking different. I could have given an example about die or a coin toss, but let's say I have a different example. So let there be 240 television sets, and 15 of them, let's say, are defective. They're not working. Defective. Okay. Now you want to buy two television sets. Okay. Now, if I ask you, what is the probability that the both of them which you buy, okay, this 15 you do not know, by the way, okay, because you had gone to the shop and you saw that, okay, there are 240 television sets, so there you want to buy two. You didn't check whether they are working or not. Okay, you just bought it. So you pick two of them, and then and you do not know that there are 15 defective television sets. So my question is, what is the probability? What is the probability? Probability that both. Oh, I did not write. Okay, now suppose. Okay, let me complete the question. So let I want to buy two television sets. Okay. Oh, television sets. Or I buy two televisions. Forget I want to. I buy two television sets. The question is, what is the probability that both are defective? Now, this question will answer what is the meaning of this. Okay. Now, so what is the probability of, so suppose that probability of being defective is equally likely. Let us add that example, that assumption also. Okay, let us also assume that. Being defective, okay, This can happen with defective happen with equal probability. Equal probability. Let us also assume this. Then what is happening? Then what is the probability that so you want to buy two television sets. So once you buy one, okay, what is the probability that it is being defective? It is 40. You have 240 television sets. 15 of them are defective. So once you buy one, then what is the probability that it is defective? Because all are equally likely, okay, of being defective. So the probability is 15 by 240 because this is 15 of them are defective. Okay. Now once you buy that, okay, the probability of that being defective is the same value here, probability. But now, once you bought that, okay, then there are 40 defective. So what will be and there are 239 television sets. So then what is the probability? So if this event has already occurred, like here, once this has occurred, okay, A occurred, okay, it's probability of A. So I am asking about this probability of A intersection B. Now A has occurred. Then once you know that A has occurred, what is the probability that B is occurring? So this is, instead of considering this as a division, you consider this as a multiplication. So A union B, both are defective. A is the first, let's say, television set, B is the second television set, and both are defective. So if once you choose this, once you buy one, then based on that, the probability of B will change. So then the answer will be what? 15 by this times 14 by 239. What would be this number? I don't know. Okay, this is something. Okay, this is the answer. So that means what? So instead of considering this as a division, if you consider this as a multiplication, what is happening is probability of A intersection B. Okay, if you see the Venn diagram, then what is happening is this is A and this is B. You are talking about this. This is A and this is B. You want to find out this intersection. Okay. Now, if A has already occurred, okay, probability of A. So I'm asking about what is the probability of A union A intersection B. So what I'm saying is probability of A intersection B is equal to if A has already occurred, okay, then given that A, okay, what is the probability that B will occur? This is what I'm doing. And so that's why it is probability of A given, B given A. Yeah, am I clear, or I need to pick some other example? Can you guys hear me?
No, sir, we understood.
Yes, sir.
We are
Okay.
clear, sir.
Okay. So, I mean, you can consider different examples also, okay, and try to see why this is let's say this is important, or how this is defined. In fact, this has a name. This formula has a name, okay, which applied to the definition is called multiplication rule. Multiplication rule. Okay. Multiplication rule. Yes. In fact,
Sir,
yeah. Okay. Go ahead.
Sir, I have a small doubt here.
Mm.
Suppose in this question we are taking event. Sir, can you please explain again what is event A and what is event B? Like event A is we
It is
finding
defective.
out, and event B is
Second one is also defective. What is happening?
okay.
Let
Sir.
me just
Sir,
make it.
sir, now,
Just a
sir,
minute. Yeah. Go ahead.
so
Yeah. Go
suppose
ahead.
I conduct this particular experiment in a different way. Suppose in this case I'm picking the first one, and then again I'm picking the second one, and we are considering. But suppose I picked both of them in the both of them together.
At the same
So
time. Yeah.
then,
At the same.
yes,
Yeah.
sir.
Yeah.
Sir, then the probability of the two pieces being defective would be something else, right?
Yes,
or
yes, yeah.
would this be the same again?
No, no, no. So the thing is here, so this is what you have to assume throughout the course. When you are picking something from some, I mean, so so I would say there is an ordering of happening of events or outcomes. Okay. So what I'm saying is you are when you are tossing a coin, okay, so you can also like tossing a coin. What I'm saying, suppose instead of 240, suppose you have six numbers, I mean six television set, and you will pick two of them. But whenever you are picking two of them, it is not, it is like you are rolling the die. Let's say there are six options. So first time it will appear, and then second time it will appear. So second time you are rolling it. So you are not rolling two times, two die at a time. If you do two at a time, then that is a different experiment. So the sample space will be correspondingly totally different. Here, what I'm saying is you can do that. That two, you can do it simultaneously. That means two things you are buying simultaneously. So your sample space will change. That means at a time, two things, you will have a pair of television sets as your sample space. So whatever 240 numbers are there, then so your sample space will be, let's say it is ordered as x1, x2, or t1, television 1, television 2, dot 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 dot, television 6, and then you are experimenting. What is your experiment now? You are picking pair of television sets. So then your sample space will change. Then based on that, how many pairs are there where both are defective? Based on that, there will be a probability. So this probability will not be equal to 15 by 240. That will be something else. And based on that, what is, whether one of them is defective, other one is not, and so on. All this. So there will be four situations where both are defective. First one is defective, second one is non-defective, or second one is defective, or you can say one of them is defective, and both are non-defective. Okay, so you have these three situations, three possible events, and based on that, again, you can calculate your probability. But whenever so this is just different problem itself. So this is a different experiment. When
Okay,
you are
sir,
picking
got
this
it.
together, you got it? Yeah, yeah. So the way the problem is given to me here, you are buying. I'm saying you are buying two, so you are buying the first one and the second one. Okay, this is what standard in general will follow. But if you want to say at both of them together, I want to buy, so I have to frame the problem differently. Okay, then I will have a different samples and so on. So that's why if you toss a coin, H and T, okay, so you get one outcome. But if you toss two coins simultaneously, then your sample space will change. Okay, yeah. So okay, so
Sir,
yeah.
sir, can you again explain the multiplication rule? I did not understand, sir.
So this is from the definition of conditional probability. Conditional probability. So I said this is, so this I gave as a definition. This is my definition here. So this is what is called. How did I define it? Here. So this is my definition. Okay, conditional probability. So then you see, if this is the case, then probability of A intersection B is nothing but probability of B given A times PA. This is what is called multiplication rule. This is what I'm saying. It's the same thing. Using this definition, what you get? So this goes here. Then PA intersection B is equal to PA times P of B given A. This is what is called multiplication rule. You understand? I'm just giving it
Yes,
a
sir.
name because this is standard name. Yeah. This is a very standard name. So even we will generalize it anyway, but this is just a simple name which people use, and we'll generalize this. But let us call this is the multiplication. Yeah, this is called the multiplication rule. Okay. Okay. Another situation could be, because you asked me. So let us consider another problem. Okay, and this problem let's say you are randomly picking up. Here the word random is very dangerous. Okay, as we explained it in lecture 1, by random, okay, it is not properly defined. But whenever we'll say random in for example in your 10+2 test books, or in some basic and undergraduate level books, textbooks on probability statistics, by random they always mean it is equally likely. Okay, so I must say it here somewhere. So whenever we use the word random, okay, this in a sense, because random cannot be defined, so So let's say random, whenever we use this word random, it means equally likely. The probabilities are equally likely events, okay, or equally likely outcomes. This is what is the meaning of random in this context, in the context of this course. In the otherwise it will be mentioned, okay, that randomly with probability this and something like this. If it is not equally likely, then it will be mentioned in the context of this course. If otherwise it is not, it's not mentioned. So if it is not mentioned otherwise, then we by random we always mean no, it is not mentioned, then it is equally likely. Okay, so let us consider the following problem. So let us say I pick so I have a set of cards, a deck of, let's say, 52 playing cards, and let's say ordinary cards I have, and let us say I want to randomly pick. Okay, I'm randomly drawing 2 cards. Okay, and let's say 2 asses in succession. Okay, so or maybe I'm just picking two cards, and then the question is, okay, let me frame the question then. So the question itself say determine the probability, okay, of drawing 2 aces, okay, randomly from a deck of 52 cards, or let's say playing cards. Okay, so what is the probability? So number of aces is what? Number of aces is 4. Okay, so then you see there are 2 things here. One is once you pick the ace, okay, one particular card, suppose it is ace. So there are 52 choices you can pick, and 4 of them are only aces, and they all are equally likely. That means what is the sample space? 1 to, if you just number the cards, it is like 1 to up to 52, and there are 4 cards which are like numbered as aces. Okay, then what is the probability that if you pick one of them, it will be S? So because everything is equally likely here, so getting one S is 1 by, here is 4 by 52. Okay, that 4 of them are for SS out of 52. Okay, this is equally likely. So the first one is, of course, 1 by 52, because for picking any card is probability is 1 by 52. Okay, they are equally likely. So the one S is also 1 by 52. The other S is also 1 by 52. Other S is also, and the other one, the last one is also. So if we just sum it up, so there are 4 S's. So once you pick a card out of this 52, the S will be the chosen one, the chosen card will be an S of any color. Okay, will be 4 by 52. That's true. Now there can be 2 things. One is you again pick that card back inside the deck, or you don't do it. Okay, so there are 2 situations here now. So whenever this kind of problems are given, then so there are 2 situations, let's say. Then there are 2 situations. So the television said there is no replacement, but here let's say there can be another option, another experiment, like where you want to replace that and you want to do it without any replacement. Okay, there are 2 situations. One is, let's say, without replacement, and another one is with replacement. Okay, now you want to find out. So what is the solution? So for this, first we consider without replacement. So you don't want to replace this. Okay, then what is that? Once you pick the first card, okay, now since picking any card, because it is equally likely, any card is the probability, and since the probability of any any particular card, whatever it is, okay, all possible cards we have, is 1 by 52 the probability of let me extend this a bit, yeah, probability of choosing or picking an ace is 4 by 52. Now once you do that, and if you do not replace it, and my original question was, what is the probability that two successive cards are chosen and both are S? Okay, so once you do that, once you pick the first one, the probability of having this as an ace is 452. And if you do not do the replacement, and this has all card, okay, so you are using the conditional probability here. This has occurred, so this is the first event. Okay, let's say that this event is A. If that has occurred, then what is the probability that the next time when you are picking the second card, okay, that will also be an S. So what is the probability of that? If this is occurred, okay, then the probability will be remaining card is 51, and out of them 3 are S's. So this is the answer. This is without replacement. And if you want to do with replacement, then what will happen? This will be just 4, 5, 58, 2 times 4, 5, 58, 2. Okay, so 452. So this is an example of the multiplication rule or of the conditional probability. Whenever there is a situation where the experiment is without replacement and you are doing it for many times, let's say 2 times, 3 times, 4 times, then every time you have to use the conditional probability. Now let's say instead of 2 cards, I can also say I am to pick 3 successive cards. And what is the probability that all of them are S's? Okay, so then what do you have to do? So the A occurred. Okay, so then I have to consider the situation. So if instead of 2 cards drawn successively, let or consider consider 3 cards are drawn successively. Then what happens? Then I have 3 events. Okay, then I have 3 events A, B, C. Then I have to consider that A has happened. This is for the first card. Then if it is drawn, then I have to consider another event for the second card. When A is happened, this is for the second card without replacement. I'm saying second card, and then if these also I do not replace, then I have another thing, which is my third event when both of them have happened. Okay, so it is another event. It is for the third card. So I can actually generalize the multiplication rule. So this I'll write it as a theorem because it can be also derived using just a little bit of algebra of sets. But let us say that if A, B, C are events, okay, such that probability of intersection B is not equal to 0, then probability of A given B given C is the probability of A times probability of B given A times probability of C given A intersection B. This is just by using simple algebra of sets, Venn diagram, you can also prove that this is the case. Okay, it is just the extension of the previous multiplication rule, which comes from this definition of conditional probability. Here you had 2 events A and B. Now I can have 3 events, and then accordingly one extra term will get added here. Okay, so instead of 2 cards, if I draw 3 cards, then again I have to multiply without replacement. Then I have to again multiply with so here then again there will be another multiplication which is 2 by 50, right? This will be again multiplied here. Anyway, so yeah, so let us consider another example, maybe. Okay, maybe not. Okay, this is just just the same thing I'm saying. So I can extend it for a1 a2. So instead of I can say it is a1 intersection a2 dot intersection ak, and then what is the rule? I'll talk about that, but before that, let us say let us just recall what did we say? We say we considered a situation before we introduced the concept of conditional probability. Okay, we considered a problem, and the problem was uh, what is the salary in Bihar? What is the salary or annual salary of a teacher? Okay, is it more than 5 lakhs? Now see, if you have chosen a very nice sample space, okay, a sample space means, okay, the number of teachers, number of schools, number of college, university, they are all equal. I mean, they're in a nice proportion in your sample space. Then it may happen that it does not matter whether it is school or it is college or university, your answer is always right. That could happen, but happening of this is rare. Okay, but that could happen because the same answer we're getting doesn't matter whether you restrict yourself to mm, uh, your, let's say, mm, school or college or university. Or maybe I can pick a different example. Like suppose I ask the same question, but my sample space here is teachers who teach in, let's say, in KB, the Kendriya Vidyalaya, let's say. Okay, it's in KB. Or maybe any school where the salary is decided by an authority throughout India. Okay, then let's say in IIT. Okay, so then it is decided by the government or by whatever. Okay, throughout India. So then it doesn't matter whether you consider a teacher or a faculty member from IIT Bombay or Delhi or Kharagpur, doesn't matter. Based on certain rules, their salary, okay, is fixed. Okay, so it does not matter. So even if I give you an additional information, like let's say what is the salary, okay, of probability that the salary is more than 5 lakh in IIT Bombay, maybe the same thing, same probability will also occur in IIT Kharagpur or in IIT Delhi because the salary is decided by a set of same rules. So that means additional information need not always change the probability. Okay, in general it should change. That's an intuition, but this need not change. If it need not change, that means additional information does not affect your probability, and that means whatever I supplied you, the information, okay, that is nothing to do with the probability of the event you're considering. Okay, so that means that additional information, okay, has no effect on the probability of the event you are considering, right? So then we'll call those two different events, like this two different, the event which you are considering and the event whose information is supplied to you. Then these two events, okay, these two events are independent when the probability of one does not affect on the, or the occurrence of one does not affect on the probability of the other one. Okay, so we'll say, so here recall that probability of, let's say, B given A was equal to, or maybe let me write it this way, instead of division, let me write it probability of A in this is equal to probability of A and this in times probability of B in this, or you can also say this is probability of B times A given B. Okay. Now I say this is my new definition. Two events, let's say A and B, okay, they are let's say called, or they are said to be, they are said to be independent. Okay, if probability of A intersection B is equal to probability of A times probability of B. So what it means is, see here. So I said probability of intersection B, this is my multiplication rule or the definition of conditional probability, is probability of A times probability of B times B given that A has occurred. Now I'm saying if you replace this by probability of B, that means occurrence of A does not change the probability of occurrence of B. Then we have this equality. So that means I would say there are two events A and B, they are independent. Okay, if the probability of occurrence of the occurrence of a particular event, okay, and does not affect the probability of the occurring of the other event, then we'll say they are independent. Same thing is like here. So A plus union B is equal to, I'm saying, P of B times P of A. That means this has to be equal to P of A. So that means occurrence of B does not affect on the probability of occurrence of A. Then I'll say these two events are independent events. Okay. Uh, okay. So let us see an example. Maybe that will be helpful for some of you. So let's say let us consider an experiment. Let us say I have a coin, and this, let's say a coin is tossed 3 times. A coin is tossed, let's say, 3 times. So if I toss a coin 3 times, then I will have 3 outcomes. Okay, a sequence of 3 outcomes. Okay. Now let us consider the following event. Let A be the event. Let A be the event. Okay, which is like in which head occurs. Head occurs. Okay. In first 2 tosses, because I'm tossing the coin 3 times. In the first 2 tosses, first 2 times, let's say head occurs, and B the event. So B is the event, and that, let's say, in which a tail occurs, okay, on the third toss. And consider another event C. This is the event. This is the event. Okay, such that exactly, let's say, exactly 2 tails occur in 3 tosses. So my question is now, are these event, let's say A and B, are they independent? Are they independent? Or maybe let's say B and C, are they independent? If they are not independent, they are called dependent. Are they independent? That's my question. So what I'm doing here, so I have a coin. So I'm tossing the coin 3 times. And what are the events here? A is the event, that's the first 2 times, the tossing of the first 2 times. Both the times, let's say, head occurs, and B is the time. B is the event, so occurs in first 2 tosses, and B, like the third time when you are tossing the coin for the third time, then tail occurs on the third, and you don't care what happened in the first two tosses. And here also, when you're considering event A, you don't care what happens in the next toss, like in the third toss, what is the outcome of the third toss. And C is the total number of heads, total number of tails, okay, is 2 in the when you are tossing 3 times. Then my question is whether A and B are independent or not, B and C are independent or not. So if I want to answer this question, as I say always, if you want to answer a question, they always have to first consider what is the sample space. So what is the sample space here, or possible outcome? So the experiment is about 3 times tossing of a coin. So you will have outcomes like this: H, that means head, head, head. You can have head, head, tail. You can have head, tail, head. You can have tail, head, head. You can have head, tail, tail. You can have tail, head, tail. What else? You can have tail, tail, head. And you can have tail, tail, tail. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay. This is the sample space. These are the possible outcomes of the experiment. Okay. Now, what is A here? A here is first 2 times head. That means it can be this. Okay. And this can, or it can be this. That's it. This is the event A. I mean, A occurs means either 3 heads, 3 times head, or first 2 times head and third time is tail. B occurs means what? Here B means tail occurs on the third. So it could be HHT or HTT or THT or TTT. And C is what? This is total number of occurring or tail is 2. So it could be HTT or THT or TTH. Now the question is whether A and B are independent or not. So how do we check? We need to check whether probability of A intersection B is equal to probability of A times probability of B or not. So what is your guess?
A and B are independent.
Independent, sir.
In both the cases they are independent.
Only first case are independent. Second case is
The first
dependent.
case.
Yeah, second case you can check that using this definition that the first case, like this case, okay, this will be independent, and here it will not be independent. Okay, it will be dependent. You can check using the definition. So when do we say independent? So it means probability of A intersection B. This should be called probability of A times probability of B. Okay. And if it is not, then it is dependent. Okay. So, and another simple observation from this independent thing, you can say whether it is this is also a theorem, but anyway, you can also prove it, or you can maybe it is obvious that if A and B are independent events, B are independent, then A and B complement are also independent. Can anybody tell me how it is possible? B to the power C means B complement, or you can write B dashed. Okay, B complement are also independent. Can anybody tell me?
Sir, that's because first of all, we know that A does not depend on the occurrence of B. So A does not care if B has occurred or not occurred. Its probability will still be the same. That's why.
Okay, can anybody give a mathematical proof of this? You can also try to give a mathematical proof. What do I mean by mathematical proof? So consider A and B two events, and the given is that. So if you want to prove this, so So you have to say, you have to assume, so let P of A intersection B is equal to PA times PB, and then the claim is, then the claim here, the element you want to prove is probability of A intersection B dash or B complement is equal to probability of A times probability of B complement, which is equal to, you can say, probability of A times B complement is already know 1 minus probability of B. So what you want to show is it is PA, okay, minus PA times PB. This is what you want to show. Okay. Now you have to show this using the properties of the postulates, okay, or the properties whatever we have discussed. So I'll give you a hint, okay, if you want to do a mathematical proof. Hint is you write A to be equal to A intersection B union A intersection B dashed. Okay. So this is what is my hint. Using this, you can prove that. Okay. In fact, if you have more than, so let us say that this is a definition. If you have more than two events, okay, so let A1, A2, dot, okay, AK. Let this be so uh, okay, so let me change this language. So if we have more than two events, then I will say this event, the events A1, A2, AK, they are said to be independent, are said to be independent. Okay. Uh, if and only if, or just if the probability. What do you think? What should be the definition? So two events we know that probability of A intersection B is equal to probability of A times probability of B. But here I'm saying, okay, there are, let's say, 3, 4, 5, 6 events, and they are all independent. That means occurrence of any number of independence among this does not affect the probability of the occurrence of the other events, the remaining events. Right? So that has to be the meaning. So let us express this in words. Say the probability of the intersection intersections of any, let's say 2, 3, whatever, okay, so any less than k or less equal to, okay, need not be equal to, but or you can say less than, doesn't matter, k events, okay, equals the product of, or here you can also write less than equal to, write it equal to the product of their respective probability, their probabilities. Okay. So that is the thing. Now we are maybe, yeah, we'll stop here and then we'll continue tomorrow. If you have any questions, you can ask me now. Or if you have question, if you are watching this video later on, if you have questions, so you can type it in the Microsoft Teams, and then I'll get back to you. Okay.
Hello, sir.
Yeah, please.
Sir, can I say that the probability of A given B is the same as the probability of B which is inside of A? Like how much of B has occurred inside of event A? Hmm?
Okay, so basically, I mean, if I understood you correctly, so or you're trying to say probability of A given B is equal to, so if we have this, if I draw the Venn diagram, this and this. So this part, this is A intersection B, probability of the B which is inside A. That means this is probability of A
Yes, sir.
intersection B. But it is not. This is not this. In fact, this equals to this times something else, like probability of A or probability of B. Probability of B here.
Okay.
See, see. So this is little non-trivial. It means how does the occurrence of B influence the occurrence of A? So it is not equal to this, like how much it is inside this. Okay, for example, I mean, it is not like if you want me to give you a practical situation, like let's say you go to attend the classes, and suppose some days it is raining. Now, assuming that it is raining, or given the fact that it is raining, what is the probability that you will go to the class? And this, it is not equal to just probability of like raining and going to school, going to attend the class. It is not equal, because sometimes it's raining heavily. Let's say, I mean, to be very informally, let's say, sometimes it's raining heavily, then you will not go. Sometimes it is not. Is mild, let's say. Okay, it says drizzling, let's say. Then you'll go. So depending on other facts. So how the occurrence of this raining, okay, influences. Okay, how does it influence of the occurrence of the other event? That means the other one has happened, and then this is happening. So these are not actually equal.
Okay,
So
sir.
the best way to understand is, the best way to understand is this equals to this. Let's say A or B, whatever you want to write. Let's say B, probability of A given B. So that means B occurred and this. So unless you have both the informations, you cannot say anything about this. So both are occurring, and the occurrence of one of these events, okay, that can give you an idea about what is the occurrence of this. For example, in my example, you also need to know what is the probability that it will occur. It will be raining. This is one thing, and both the thing are happening. Then you can find this one. Otherwise, what is the probability that you will attend the class, and what is the probability it is raining and you are attending? Then only you will give it. You will get this thing. So both the things. I mean, so you need additional information. Yeah.
Sir,
Yeah.
so can you explain the last part which you told?
Okay. So what I'm saying is, you are going to school, you are going to attend the class, and it is raining. Okay. So A is the event. Let's say attending the class. This is what you are asking, right? Attending the
Yes,
class,
sir.
and here it is raining. So what I'm saying is, in order to find out this, that if it is raining, then what is the probability that you will go to the class? Okay. In
Hmm.
order to know this, you need to have the information of this, what is the probability that it will rain, and also raining and you are going. Okay. Both the information are required. Only this is not sufficient. This is what I'm trying to say. Yeah, like good old days, somebody
Sir,
say.
actually, uh,
Yeah.
sir, what is the difference between this part, the probability of A given B and the probability of A intersection B in this particular context?
Yeah, this is even right. Attending the class
Hmm.
and it is raining. So this is A intersection B. Both are happening.
Okay.
That you okay. And A given means given that A is raining, what is the probability that you will attend the class? This is A given B.
Okay, so in A intersection B, A and B have already happened, or
Yes,
uh,
yes, yes. Both are occurring at the same time. What is the problem? I mean, suppose, see,
okay,
if you want to answer this question, so you have to have a history of data. You have a historical data, let's say, how many days like it rained, and you also had gone to the school, gone to attend the lectures, okay, and so on, like good old days. So once you have that, then you have, let's say, an idea, okay, about what is the meaning of this. So probably you define what is this, and what is the probability that it will rain. Both the things are there. And then the question is, now the new day comes, okay, tomorrow, let's say, tomorrow it is now raining. You get to know that it is raining. Then what is the probability that you will go and attend the class? In order to answer this, you need to have both of this. This is what I'm saying. So the
yes,
thing is, yeah, okay, so I got it. Okay. Okay, anything else?
Sir,
Hmm.
sir, can you download the attendance, sir? We have another class from 10.
Oh, yes. Yeah. Sure. Please go ahead, guys. Okay, if you have class, please go ahead, and I'll end the meeting now. Okay. Bye, guys. Tomorrow, let us meet tomorrow. Yeah. Sure. Okay.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.